Hey everyone. Before launching into the new method of integration, I want to give you a little bit of a cheat sheet for integration by parts. Listed here are a bunch of integrals that we would use integration by parts to solve, and I'm showing them along with the correct component to let equal to u. So for the green box, let u equal ln of x. Notice that all those expressions have log functions. The first letter in the acronym late. In the second box, the purple box, we would let u equal x. In all of those, there's no log functions, but there's either algebraic terms and exponentials or algebraic terms and trig. In the red box, we would let u equal a trig function, and all of those are combinations of exponentials and trigs. And in the orange box, you'll see that box is empty. There's no, it's not that there isn't a situation where you would use an exponential function for u. It's just that it's very rare. And for this course, you would not let u equal, let's say, e to the x or e to the 3x or 5 to the x unless you were asked to do so. I've also color-coded some of these with blue. And what the blue color coding means is that integration by parts will have to be used more than once. There's some of these that are fairly challenging to solve, even knowing this. So that would be this box here, very challenging. I didn't do any examples of those. And other than that, the rest of these are okay. Other than that red box, the rest of these are pretty normal. And it can be done with one or two or some number of cycles of integration by parts. Anyways, on to the new topic, the advertised topic, and that's using partial fractions to do integration. Truth is that this isn't really a method of integration. This is a method for doing the decomposition of a rational function. What we'll do is we'll take an expression like 1 over x squared minus x and rewrite it as a sum or difference of two other simpler rational functions. Partial fractions is something you could have learned immediately after learning about rational functions. As soon as you learned, even before that, you could have learned about partial fractions when you learned about fractions. It's a topic that is generally held back, however. Today, it's held back until first year University of Mathematics. It works as follows. You know how to make common denominators, right? Like if I wanted to add, let's say, a over x plus 4 plus b over x minus 3, I would take the first fraction, multiply top and bottom by x minus 3, take the second fraction, multiply top and bottom by x plus 4, simplify the numerators, then it would be top plus top divided by the common bottom, x plus 4 times x minus 3. What we do in the partial fractions decomposition is we work that process backwards. We go in reverse. We start with a common denominator expression, and we split it into a sum or difference of two expressions. In order for this to work, we have to be able to factor the denominator of the original expression. So in the example I have written here, it's pre-factored, but it could have been written as 3x plus 5 over x squared plus x minus 12. We want to find out how we could write this as a over x plus 4 plus b over x minus 3. So a constant over one of the factors plus another constant over the other factor. Where these constants are unknown, but we'll find them. We'll find out what they are. There's a variety of methods that can be used to find what the coefficients are. I'm going to show you two methods and let you pick your favorite one. Now I'll start by multiplying both sides, every single piece, by x plus 4 and by x minus 3. So x plus 4, x minus 3, x plus 4, x minus 3. So I'm just multiplying the top by that. I have to do the same thing over here. A times x plus 4 times x minus 3 over x plus 4. I'll put brackets around that term. And then plus b times x plus 4 times x minus 3 over x minus 3. So all I did is multiplying, every piece by every side by the same thing, which is something you're always allowed to do. It maintains the equal sign. Now we can cancel pieces that cancel. Oh, I did a mistake. That does not cancel. Went to the wrong one. The next part cancels. X minus 3 top and bottom of the next fraction. And look how this has been transformed. Now we have 3x plus 5 is equal to a times x minus 3 plus b times x plus 4. And this must be true for all x. In particular, well, actually, I'm thinking about the second method, but so what I'm going to do next is I'm going to expand those two statements on the right and multiply the a and the b into each of those brackets. So we have ax minus 3a plus bx plus 4b. Then I'm going to do some collecting of like terms. I have an ax plus a bx. I can rewrite that as a plus b times x. And then I have a plus a constant term, negative 3a plus 4b. So if you think about this logically, I have 3x plus 5, so constant times x plus 5 is equal to constant times x plus constant. If this is true for all values of x, then the part that's in front of the 3 on the left-hand side, so the part that's in front of the x on the left-hand side, must be equal to 3. Like this part, this 3 must be equal to a plus b. Part in front of x has to equal the part in front of x. And the constant has to equal the constant. The 5 has to equal negative 3 plus 4b. So we can use that to make a system of equations. So what we have is we have 3 is equal to a plus b, and 5 is equal to negative 3a plus 4b. I'm going to take the first equation and rearrange it and isolate for either a or b. I'm going to pick a, isolate for a. So a is equal to 3 minus b. And I'll plug that into the second equation. So 5 is equal to negative 3 times, I'm going to replace the a by 3 minus b plus 4b. Simplify. 5 is equal to negative 9 plus 3b plus 4b. I'm going to add 9 to both sides, so 14. And then 3b plus 4b is 7b. Then divide both sides by 7, so b is equal to 2. Now I'm going to go back to my statement about a. This tells me that a is equal to 3 minus 2, which is 1. And we're done. We can make our conclusion. Thus, 3x plus 5 over x plus 4 times x minus 3 is equal to a, which is 1, over x plus 4, plus b, which is 2, over x minus 3. And to check, we can make a common denominators. So multiply top and bottom of the first piece by x minus 3. So we just have an x minus 3 up there. Multiply top and bottom of the second piece by x plus 4. So we have a 2x plus 8 there. So on top we have x minus 3 plus 2x plus 8. and then simplify x plus 2x, 3x, negative 3 plus 8, 5, and there's our 3x plus 5. Just as a quick check that everything was done correctly. It's just uncommoning the denominator. And I think that's worth writing down, that we are uncommoning the denominator, uncommoning the denominator. I bet you didn't know we could do that. We can go take something with a common denominator and split it up. Here's the second approach for finding the coefficients a and b, and I think you're going to like this approach better. It starts the same way, 3x plus 5 over x plus 4 times x minus 3 multiplied by x plus 4 multiplied by x minus 3 equals a times x plus 4 times x minus 3 over x plus 4 plus b. We already did this, but I want to be fair. I want to show both methods in full so that you can compare the writing appropriately to see which one's more work, which one's less work. So I'm going to cancel the x minus 3, cancel this x minus 3, cancel the x plus 4s. I have the same statement we had previously. 3x plus 5 has to equal a times x minus 3 plus b times x plus 4. And this must be true for all x. And we're going to exploit that fact, that this has to be true for any x value. It has to be true for 0. If I plug in 0 on the left and 0 on the right, it has to work. So if I do that, I'll have 3 times 0 plus 5. So 5 is equal to negative 3a plus 4b. Not too helpful. It's true for x is equal to 1, x is equal to 2, and so on. If we're smart, we can choose an x value that will take our expression that has 2 unknowns in it and result in only one unknown surviving. So choose a smart x value. What's smart? What does that mean? A smart x value is one that makes either the a term, the a times x minus 3, or the b term, the b times x plus 4, completely disappear. Because then we'd just be able to solve for the other one. So here's what I consider smart. Let's choose x equals 3. It's smart because the first term, a times x minus 3, becomes 0. Now this has to be substituted in everywhere. So 3 times 3 plus 5 is equal to a times 3 minus 3 plus b times 3 plus 4. So we get 14 is equal to 7b, and we immediately get that b is equal to 2. All right, now how do I get a? What choice will naturally lead to a? Look at the second term on the right. I want to make b times x plus 4. I want to make that part disappear. What x value do I need? Well, how about x equals negative 4? So if I make that choice, so 3 times negative 4 plus 5 is equal to a times negative 4 minus 3 plus b times negative 4 plus 4. Then simplify, we have negative 12 plus 5, so negative 7 is equal to negative 7a plus 0. So that tells us that negative 7 is equal to negative 7a. I'll put b times 0, I guess. And that means that a is equal to 1. We'll divide both sides by 7. Or negative 7. So thus 3x plus 5 over x plus 4 times x minus 3 is equal to a over x plus 4 plus b over x minus 3. Got the same answer. Oh, I got the a and the b in. What am I doing? So a is 1 and b is 2. We found the same answer as the last example, 1 and 2. I have some things to be careful about when you're doing these. When you make your final conclusion, make sure you match up the right coefficient with the right component. That the a has to go on top of the x plus 4. That's what we called it. Now we could have switched the order of those terms. Someone else could have written their factors as a over x minus 3 plus b over x plus 4, and their a and b values would have been flipped as well. So don't worry about that. There's no correct order as long as you maintain that correspondence at the end. So don't change your mind after you make a choice. Don't change your mind and say, well, actually, I'm going to put this a over here. You just have to be consistent as you go through the problem. Okay, for the next example, I'm not going to use the first method. I'm only going to use method 2. So you're on your own if you want to use the first method. Don't use the first method. It's harder. It's more work and more likely to make a mistake. The second method, to choose the smart x value method, is always going to be faster. For this course, for the problems that we do in this course. Anyways, next example, 1 over x times x plus 1 is equal to a over x plus b over x plus 1. So that's the way it splits. It's a constant over the first factor plus a different constant over the second factor. We multiply both sides by x, we multiply both sides by x plus 1 and cancel everything that cancels. And what you'll find is every time we do this, it'll look like this. We'll have, on the left-hand side, the denominator vanishes. On the right-hand side, we'll have a multiplied by the bottom of the second term plus b multiplied by the bottom of the first term. Okay, this is true for all values of x. Choose smart x values. So here's my choice. I'm looking at it thinking, well, I want one of those terms to disappear. So what if x is negative 1? That'll make the first term disappear. So we get 1 is equal to, and we've replaced all the x's with negative 1s. There's no x on the left-hand side, so there's nothing to replace there. On the right-hand side, we have a times negative 1 plus 1 plus b times negative 1. So 1 is equal to 0 minus b. We can divide both sides by negative 1, and we get b equals negative 1. Now, how do I get the other coefficient? Well, what if I let x equal 0? That'll make the second term disappear. So 1 is equal to a times 0 plus 1 plus b times 0. So 1 is equal to a. Well, that's done. Nothing to do. Don't even have to divide. A is just equal to 1. And we can make our conclusion. Thus, 1 over x times x plus 1 is equal to a over x, so 1 over x, plus negative 1 over x plus 1, which is equivalent to 1 over x minus 1 over x plus 1. Just bring the negative out front. And then to check, make common denominators. Make sure you recover what you originally started with. The next part's still part of the introduction of this method of partial fractions, and this slide isn't tested. But I want to tell you that it can be extended further, that you can do more than what we do in the course with these partial fraction decompositions. There's lots to know about factoring, lots to know about some of the theory behind what I'm about to describe, but since it's not part of the course, I only want to go so deep into this. Any polynomial, no matter how high order it is, can be decomposed into a product of linear terms and irreducible quadratic terms. An irreducible quadratic term is a term that is quadratic, so x to the power of 2 is the highest power of x, that has a negative discriminant. So that means you cannot factor it into subsequent linear terms. So for example, x squared plus x plus 1. If you try to use a quadratic formula to get what the roots are, you'd find that the roots are imaginary. You have the square root of negative numbers. So we would call that, in a course that does not deal with imaginary numbers, we would call that a irreducible quadratic. It cannot be factored. Another irreducible quadratic would be x squared plus 4. You cannot factor that into two linear terms. So it's possible, no matter how nasty the polynomial is, you can write it as that product of pieces. So a simple one, x squared minus 1, you can write that as x minus 1 times x plus 1, a product of linear terms. X cubed minus 1, so a cubic, you can write that as a product of a linear term and a quadratic term, x minus 1 times x squared plus x plus 1. Foil it out if you don't believe me. Now in this course, we stick with quadratic factoring. We don't do cubic factoring. But I mean general cubics, x power 3 plus 5x squared plus x plus 5, it factors into a linear times a quadratic. X cubed plus 1 factors into a linear times a quadratic. X to the power 4 minus 1 factors into a irreducible quadratic and two linear terms. X to the power 4 plus 1 factors into two irreducible quadratics. It doesn't matter how nasty the polynomial is, you can factor it into this way. So if you have a rational function of the form p of x over q of x, so a polynomial on top and a polynomial on the bottom, you take the bottom polynomial and you write it as a product of linear terms and quadratic terms. Then you can use partial fractions or a partial fraction decomposition to write it as a constant over each of the linear terms as many times as they appear, plus a linear term divided by each of the irreducible quadratic terms. So we don't have the nasty case that's indicated here. We don't get that deep into the decomposition. We will only have two linear terms in our decomposition. We'll have a polynomial on top and a quadratic with two nice factors in the bottom. And I'll pause here and continue with examples in the next video.